So let me just remind of the four flavors. The first two flavors: collapse on other flow and strong collapse on other flow. Collapse is for strong. Where you have, well, you're gonna have the phi t is gonna be a topological another flow. So another flow maybe weaker regularity, a self-orbit equivalence of that flow. So it's a homeomorphic sense orbits to orbits. And a semi-conjugacy, so H. So H from M to M is homotopic to the identity and gives the semi-conjugacy. There are different conditions, strong condition, of course, here, because here you're using the branching foliation CS and CU. Here, just the flow lines and things which are tangent to the center. Correct. The leaf space, we have just a homeomorphism. So this is homeo, which is I1 invariant between the orbit space of the another flow, which I said is always homeomorphic to R2, and the leaf space, the center leaf space, which is the intersections of CS and CU leaves in the universal connected components of this. And finally, the quasi-geodesic part of the hyperbolic, which is just geometry. We're gonna have the branching foliations. We're gonna assume here that they have Gromov hyperbolic leaves, and then the center leaves are gonna have the uniform quasi-geodesics in the two-dimensional branching leaf, the CSC. By the way, I don't know if I did this. This is the center foliation, WC, which is the WCS intersected with the WC. Okay. All right. So and then I gave I said that under conditions orientability conditions, these three are equivalent. They are the same. Okay. And also I talked about some applications, accessibility, et cetera, et cetera. So I'm going to go over these topics today, the first and second lecture. I'm going to start with the applications, and hopefully we'll have time to do some of these equivalences. So we'll see how that goes. Okay. So first of all, let's see. Right. So let me start with one thing here. So here we just have a self-orbit equivalence. Here we do not have a self-orbit equivalence. So first of all, let's say where is the self-orbit equivalence? The flow here. If they're going to be equivalent, they're going to have a self-orbit. So this is very easy to get. So let's start with that. So yes. So F tilde with F the cover and define map. And, so this is going to be from the orbit space itself, which is going to be H inverse. So H is a homeomorphism from the orbit space to the center leaf space. Now F tilde, this is obviously so induces homeo of LC to itself. And then H versus the homomorphism. So this is, yes, no, this is the homomorphism of the orbit space. And it is I1 of M invariant. Let's see, I'm just gonna do the formulas. There is a homomorphism on I1 of M itself, which will be, you take this lift, F tilde, okay? And then this formula here. So this O is an orbit, gamma is an element of I1 M. This is okay. So there's this pi1 equivariance here. So this implies then by results of Heffliger. It's a homeomorphism of the leaf space of this foliation universal curve. The foliation by flow lines universal curve. So the results are Heffliger, G's, and Babot. There is homeomorphism of the manifold sending orbits to orbits inducing this. Okay. So that's how you construct a self-orbit equivalence of the flow in this case. And obviously you can see that the beta is related to the F, because it's coming from the action of the F. So even though it's not explicitly there, it's very easy to get. Okay. All right. So any questions? All right. So I'm gonna start. So the applications are going to be sort of the open for the EAF. And after I'm going to go over a little more of the leaf space case, because that's a little sort of easier to expose. Now I'm going to use a technical result, which depends on the result of HBS. So the first few. Then I'm going to do the accessibility. Then I'm going to talk about the hyperbolic and hyperbolic union. The first lecture, but hopefully I'll get to the third thing first lecture and maybe a little more in the second one. Okay, all right. So first open close property. So we use a result technical. We're just gonna state this, but I'm not gonna say anything about it. So uniform form of results of HB. So here's the result. So this result is going to say that there's a neighborhood. For every F, there's a neighborhood of that F, so that if some element in the neighborhood satisfies the probably has branching foliation, then no elements in that neighborhood have branching foliation, and have branching foliation with regards to very related to the branching foliation of one. Okay. So let me state this. Yes. Yes. Right. Right. Yes. Yeah, definitely. In that sentence, no. The point is that you do the branching foliation. All right, so let me think that there is an open U zero P1 topology and epsilon greater than 0. Every and U is pH, so that's the part that's just transversality. And if for some the U there is a branching foliation. And then choose the S, variant under G. Then for every prime in U, there is similarly a branching foliation for G prime. And epsilon equivalent to the epsilon equivalent means very close. So epsilon equivalent means so there is a homeo between leaf spaces let's call it mu. So that L L epsilon Hauser distance apart plus also tangent bundles sort of epsilon close. Okay. So here's sort of one of them, and then take L and then the L to be very close. So the point of this is the uniformity. So once you get one element G there, which has a branch foliation, then so the same thing works for all them in that neighborhood, and they're all sort of okay. Question on the statement, what do you mean? Right. So I'm gonna do the argument for the LS CAF. And there's an argument also for the CAF, which involves a similar statement for now for the one-dimensional center foliations, but that turns out that to get the result is harder in that case. So I'm going to go over the LCAF. So, so first I need the proposition. So we start with an F. There's a neighborhood U, which is going to be exactly that neighborhood. E U, which is L E M. With respect to topological coordinates of phi of T. That's going to be data. So I said that if you have a least space collapse on the flow, there is a SOE associated to it. Then for the sorry. Right. And all right, so then any define U define is also least speed flow. With respect to the same flow, same class. Beta. So SOE class. So two. Therefore, we can alpha, beta are same SOE class is alpha inverse composed with beta, which is also a self-orbit equivalence, is trivial. So Thomas mentioned what this is. So means that every orbit is fixed. Okay. Right, and this will sort of essentially immediately imply the open and closed property. The open property is in the statement already, and the closed property you just do it by sort of getting you got Gn converging to F, and so if Gn will get a neighborhood which is uniform, so you can get that. So let's see how you get this. And this will be not too hard. Let's leave that there for a moment.
Already totally have to pass the bond position.
Sorry?
Yes, to already thought that we needed on position for after the practically so it's already just to well to some kind of design.
So sorry, I'm not understanding the question.
Before we don't see euro, but we need it to pass to you.
We have to pass it. Right, we have to pass it.
Something like that already thought that we need this on position and there are some leaks for the stability.
Right. Right. Yeah, right.
Sure. Yeah, of course. Yeah.
Right. So yeah, I mean the HPGP, the rescue and shoe book is quite detailed, pretty cool. This still okay. All right. So let's see. This result is fairly simple. Once you get the uniformity result that I just erased. So let U be the neighborhood given by the technical theorem. And sort of the epsilon greater than 0, so associated with the theorem. Okay. Then since we have one G here, which is so G and U is CHF, then G has CS and CU, and then using the theorem, for any G prime and U has CS and CU branching foliations. Which are epsilon equivalent respectively to the ones of G. Okay. Right. So what I'm gonna do, so using this, it's very easy now to make a homomorphism between the center leaf spaces. And because, the G was leaf space connected on the flow, I'm going to get also a homomorphism between the orbit space of the flow for G and the center leaf space for G prime. Okay, so let me do that. So then, for any center, C, I guess, here G. Right. So it is a component L with U. So there are unique L prime and U prime. So L prime in the CS foliation U prime. And U prime in the CU foliation of G prime, which are epsilon near L and U respectively. So this implies that there is unique component C prime of the intersection of L prime and U prime, which is 2 epsilon near C. That's here. So map C to C prime. So we get a homeomorphism between these center leaf spaces. Homeomorphism leaf spaces. G prime, which is obviously I1 invariant. Let's call this tau. Okay, so we had from the orbit space of phi, we had age, onwards to the center of space or G, and then we have this tau, center is G prime. So we compose, and then you have a homeomorphism between the orbit space of the original flow and this, the center of space, and it's in, so this implies that G prime is LS the F back to the flow, and I mean it's the same couple with the graph. Just to the immediate you get the open property and you can very quickly get the closed property. All right, so let's go over now to the accessibility. All right. So here I use the least space collapse on the flow. For accessibility, I'm gonna do the collapse on the flow, hopefully, but we'll do the strong collapse on the flow in detail. Later on for the quasi-geodesic, for the hyperbolic, or the other use. So accessibility. So the accessibility class X is those Y you can get on X by concatenation of X in stable and unstable foliations, and F is accessible is the accessibility class X is equal to M, and then obviously it doesn't matter which X you're talking about. Okay? So by results of HU, and other people as well. So we three, so stability plus the necessary properties, the volume reserving plus C1 plus implies ergodicity. So here I'm going to talk about how to get accessibility, okay, under certain conditions, and so we're really not going to talk about results. So just accessibility. So there are results that said if it's not accessible, and she already used this, then you have this laminations, the lamination. So let me talk about that. If not accessible, once again is you, then there is the elimination. So this, right, I should say two-dimensional elimination. So the leaves where yes, EU, so I guess yes, plus U is applicable. Sorry? Oh, yes, right. So let's see. So I want to solvable. I guess always M3. Then in addition, in the wandering set, down. Then we have further properties that we're going to use. The complementary regions. This are I bundles. The EC is uniquely integrable. Completion. Any complementary component. And also, there are no compact groups. Right. So, in particular, now I'm going to derive some sort of three-dimensional consequences here. So these lamination can be extended to a foliation, which I'm going to denote by F. So that in complementary regions, the lamination, SU lamination, F is transverse to the center bond. Okay. All right. This is what we're going to use. Right. So, well, maybe. In particular, this foliation F has no compact leaves. Not gonna get into this in detail, but for the experts, so there's always no ray components. So what's important for us is that the leaves have filled up topological. They're properly embedded. Topological planes. And a transversal to F tilde intersects a leaf at most points. Okay. All right, so this is the setup. So the theorem. So let F be PH and 3 with line 1 of M not. Sorry. Hold on. What? Yeah, thank you. So still means live to and silver. Raw. Right. So the theorem is right. So suppose the non-wandering set back is on M. So if F is CAF, then F is accessible. So I'm gonna do the proof. Sort of in the end, it turns out that there's a simplification with the F from CAF, but hopefully I'll be able to do with the CAF or talk a little bit about the CAF as well. Okay. So the strategy is to produce a closed curve and I guess not homotopic curve in a leaf of this lamination here. So this is the sort of the end result. I'm going to go a lot of stuff here. This is the end result. So in SCAF case, the curve will be tangent to ES for EU. But yes, or EU are uniquely integrable. Therefore, this curve will be a leaf of the stable and unstable foliations. That's more possible because for ES, if you bring forwards, we will bring a very small length, so that's impossible. Okay, that's in the CFT. So in CAF case, we don't quite get that. So we need one invariant by a power of F. And that will turn out to be also impossible because either forward or backwards is going to have to increase in length. So it cannot be invariant by a power of F. Because, either it's tangent to one of these or it's transverse. If it's transverse, it's going to have some unstable component, and if you going forward, that's going to grow, going to go without bounds, so it cannot be invariant by a power. Okay, so that's the strategy. Okay, I mean the split here comes really at the end. I'll see how much time I have and so on. All right. So. Yeah. So so we have this whole program, which is the collapse on Anosov flows and all these flavors and so on. There's always topological Anosov flow in the background, but I really haven't seen properties of the Anosov flow. For this result, I will use, and I'll use some properties of the orbit space and so on and so forth. So now we use properties. So the first property if the plot is not orbitally equivalent to expansions, then there are freely homotopic closed orbits phi p. So pretty much I'm going to use this as a black box. If I try to explain this, it's going to take about 10, 15 minutes, okay? Right, so that means, let's call them, say, so lift to the lift to the universal cover, we have O1, O2 orbits, flow, which are fixed by saying non-trivial back translation. So here's O1, here's O2. So they're both invariant under G. So first of all, this is my S. This is my U. So some people in the audience already cringe. So this is no. Why? Because the intersection of S and U is unique. Because the orbit space is a plane, and I have two one-dimensional foliations in the orbit space. And let me denote them by OS and OU, and which are transverse. So when two leaves can intersect, a leaf of one of them and a leaf of the other one can intersect at most one, but they're transverse leaves. So a power G, right? So I guess the double power of G preserves this half leaf of this orbit, preserves this, so then we'll preserve this as well. Let's call this Q. So preserves Q, and therefore when you project this to the manifold, here's the orbit associated with the pi O2. And here's the orbit associated with pi Q. So I have two closed orbits here in unstable Newton composite. Okay? So you can't have this. They cannot intersect. But in some sense, they almost intersect. Or there's a sort of a collection of these from one to the other, so that consecutive leaves almost intersect. Okay? So I'm not going to get into so much detail, but this is an idea of this sort of generalized rectangles, which are called lozenges. Yes. Yeah. Yeah. No, because I think a power of G will fix the prompt. So yeah, but I am using that two intersect in the most one. Right. So it turns out that O1, O2 are connected by a collection called a chain of almost rectangle sets. These sets are called lozenges. So I'm going to draw here what happens. This is sort of in the orbit space. So we're going to say I did this. No, I didn't. So the first orbit and the next orbit, it's almost like they are the corners of a rectangle. So rectangle is this, okay? But then we imply that the unstable of this intersects the stable of this. We don't have that, but we're almost going to have that. So this is a rectangle minus 2 points. Well, this is our actual points. These are actual orbits, and these are missing points. But in the interior of this thing, I have a product structure. Okay. So it's like you take pick up a rectangle and remove this 2 orbits here. That's the topological picture that I have. This is called a lozenge. So the result is that you're going to have a collection of these, and you may have sort of a more complicated picture because you can have some of them which are actually sort of adjoining on the same side, and so on until eventually you get to the. Okay? So again, this is not a result as you're going to take it as a black box. Okay? I'll talk to you later about it if you want. Okay, so we use only one lozenge. So this was to get one lozenge. And I think I'm going to call, let's see, call this C1. No, that's the whole one. So I'm going to rename this the orbits. The orbit 1, orbit 2, and my lozenge is going to call it A. Right. So and G leaves this in there. Okay. So so here's an important fact. So if G acts in O1, so here's O1, and G leaves this invariant, but may take points forward, flow forward, or flow backwards. Okay. So if it jacks O1, sending points forward, then it acts in O2, sending points backwards. And the reason for that is the following. So look at the action. We're going to look at the action here. So, right. So G is going to fix this, and I'm thinking, yes. So G is going to fix this, and it's going to fix this prong here, and it's going to take orbit here. So it's actually going forwards. It's actually going to right. So the G is going to move this way. So that's the G here. So G, so contracts in the unstable of the first orbit, and therefore it's going to be expanding here. So if it contracts here, sends this leaf to this leaf. Therefore, here it takes this leaf to this leaf, but expanding here. So G expands in the second one. So it's the opposite direction. So in one of them is going forward, and the other one is going back. Okay. So this is going to be crucial for us. Okay. Well, we'd stay with it, you're right. Let's keep track of that. Oh, now we're going to do the other one. Okay. So what am I looking for here? So it turns out that with this, it up, I will produce some curve in each field. So either you see the W one, or you see the WS one. So we're going to project now using the H, the collapsing map, so that intersection with some E leave the SU lamination is G invariant. Okay. This is what I want to show if it holds. Now, if it was, if SCAF, then this intersection is, well, let's suppose this case, intersection. So if this is the case, though, this is the weak stable lead. S, but the H tilde of S tilde is my WCS. This is in SCAF. Okay, this is still there. So this is going to be tangent to ECS, but it's here as well. So it's tangent to the ESU. So the intersection is going to be tangent to ES, but it's G invariant. We're going to get a closed S curve in M. Okay. Now, in the case of CAF, we don't get that. So it's going to be more complicated. Let's see. All right, so let's see how to get this. So how you get D? Okay. So first of all, so now we're going to use the H tilde. So we call that the H tilde. So for collapse, maybe not in general collapse, but sends orbits to curves tangent to EC. So using this, H tilde induces a vector field Y tangent to EC. So I guess non-zero. In particular, the EC is orientable, and this uses H homotopic to the identity. So in particular, Y is transverse to my foliation M. Okay. So the first, right. So let's CI to be the H tilde OI. So the CI are now curves parallel to EC, which are transverse to the. So this, the F was the sort of filling in of the gaps of the SU lamination. So first fact is if L intersects C1, then it does not intersect C2. And this is where we're going to use the orientation reverse there. If it acts increasing in O1, then it acts decreasing in the other one. So here's my L. So L is going to be L D F2. And suppose that intersects C1. So act by G, so increases in O1. So also sends L kind of to positive side with respect to the Y. That's one tilde. Here's the one tilde, and my E of L is here. Okay. But if it intersects C2, so in C2, G acts so decreasing, sending flow backwards. And remember, the Y is everywhere. My thing is everywhere transverse. That would say that my G of L is here, but L separates. So this is impossible. Okay. So it was key that the G was actually increasing in one of the corner orbs of the velocity and it actually decreasing in the other one. All right. So pick L intersecting C1 and L in the. So I mean the complementary regions L of this lamination are I bundles where the center bundle is uniquely integral. So if I have something that intersects right here, I can just go along the C and intersect something in the lamination. Okay, so we can assume this. Okay, so here's my C1, here's my L, and then suppose that this. So either the C2 is on the positive side or on the negative side, because it doesn't intersect. So C2 intersect with L is empty. So either in positive side or negative side. So we're going to assume, without loss of generality, on positive side. So then I iterate by G to the N for N positive. It's always going to be, you know, on the positive side. So it's G of L, etc. And take limit. And in the limit, there is a unique leaf E, the lifted lamination, which separates C1 from C2. So I'm going to take this, the C2 is always here. I'll take limit, there's going to be a unique leaf here. That's what we're looking for. Okay. Finish quickly. And I'm not going to do the DAF case. All right, so this E is the leaf I'm looking for. So by definition, since it's unique and C1 is invariant by G and C2 is invariant by G, E is invariant by G. So now let's look back to our lozenge here for 1, for 2. So, and I'm gonna have a set E O is gonna be the set of let's see, elements in the orbit space, so that the H2 X intersects my leaf E. So I sort of take the pullback. So the E is transverse to the Y, which was the projection of the flow direction there. And I'm going to look at where it intersects. Okay, so I know it intersects some orbits. So the plane, so the for 1, right? So for either stable or unstable, the E O contains a half leaf. So either are OS O1 or OU O1. So I'm claiming that this contains either this or stable or this. And if you have that, then the sort of intersection E with the H tilde, the stable for 1, suppose it's stable, okay? So this is G invariant, and it's the curve I'm looking for. So 1 minute just to say, how do I get this? So how to get this claim? And obviously I already explained in the strong CF how that thing. The CF of not that. Okay? So how to get this? So it turns out that the boundary of this set is a union of stable or unstable leaves. Okay. Again, we cannot explain this. So it turns out that it has to intersect the lozenge, or else, you know, there's a pattern of 1, 2, 0, 2, and then E does not separate C1 from C2. Remember, E was a leaf to separate C1 from C2. And once that's true, so we're going to have a point here, which is in E, and obviously it's the E theta, EO, and since it's G invariant, you know, you're going to get the G images. So it contains the whole lozenge. So A is contained here. Sorry, I'm putting a lot of stuff in the below. And then using this property, so then using that the boundary has to be either full leaves of the stable or full leaves of the unstable, then the theta has to contain either 1/2 leave the stable or the unstable. Let me stop here. Thank you so much.
We will continue, but is there any quick question? When we meet again in, let's say, 5 minutes.
Okay, so for the now we have 15 minutes instead of the 1 hour, so maybe we'll be a little lighter. So you know, you're gonna have me for this, but tomorrow Thomas comes back. He's gonna talk about why the examples of GHP, or at least some of them, are a strong collapse Anosov flows. And we're going to talk a little bit about self-orbit equivalences, and perhaps the ones that are realizable. I was just saying, Thomas, I was just saying some of the topics you'll cover tomorrow. So I may have lied. Anyway, all right, so I'm going to talk about the case in hyperbolic manifolds. So here is a theorem. If F pH in M3 hyperbolic is then F is now, let's see how fast this goes. If we have time, we're going to talk about maybe one of the equivalences between the three strong flavors. Yeah, we'll see. Okay. So, by the way, again, let me remind that hyperbolic tree manifolds are the most common amongst irreducible tree manifolds. Reducible means you cannot decompose, essentially you cannot decompose the fundamental group as a free product. So they are by far the most common. So this takes some, you know, sort of you know, describes them to a certain extent in a large graph. Okay, right. So first of all, so the mapping class group M is finite. This is really a consequence of most of rigidity. So up to an iterate, we assume that F is homotropic to be identical. Now I'm gonna get some results for F. As a matter of fact, not even F. This power, and in the end, we would have to recover the results for the original map. I'm not sure how much time we're gonna have. So that sort of involves this idea of invariance of the branching correlations. Okay? So. So yes, hyperbolics overused words. So this is a partial hyperbolic. M is hyperbolic. Has a metric with constant curvature, sectional curvature is equal to -1 everywhere. Sectional curvature. Right. So again, up to a finite. So I guess another finite iterate. Could have done that already. And finite lift. Assume F has orientable BC, DS, DU, and DF preserves orientation. Again, can get results for this. And then it would have to recover for the original F. Oh, and also again, F homotopic to the identity. So it turns out that a lot of the analysis is going to be done for the case where I have a partially hyperbolic, which is homotopy to the identity. And some crucial places I have to use the dynamical hyperbolic. So the beginning, it's a little more general, but from some point on, I really have to use the dynamical hyperbolic. Okay? So first of all, we haven't talked too much about the, all right, so yes, so this implies now there are branching correlations. So again, this is Burago and Ivano, which are tangent to CSU and which are invariant. Okay? So first of all, this happens but no, not necessarily. Probably not. Not always. There's one more possibility that maybe we realize it, but there's one more theoretical. That's the goal. And that will sort of start to appear very quickly. So first of all, so here's my, I'm going to talk about the leaf spaces. So this is, yeah, so what is the leaf space this? So this turns out it's like the leaf space of the lifted cover of Raveless foliation. So this is a simply connected one manifold, but perhaps not Hauser. But this is like for Raveless foliation. I'm going to draw a lot of the pictures here as if there was no branching, just because it's sort of easier. But you know, almost all of the arguments work exactly the same. Some of the arguments like we have to do a little more work. Okay? Right. So what are we going to do now? Right. So yes. So consider the lift F to the F what is homotopy to identity. So since I'm talking a little more generally, it's always unique except in the case with cyber fiber. Okay. And in the case of cyber fiber, you may have more than one. Okay. So so pick one in the case of cyber fiber. So this F tilde is called a good lift. So two properties. One of them which will be used immediately. So F tilde commutes with all that information because it's a lift of a multiplic to the identity. And second property is that F tilde moves points a bounded distance. So there is a 0 beginning 0, so the distance between F tilde of X and X is less than a0 for any X in the universe. So here's the first fact. Suppose that L is in leaf there, and I want to understand whether. So Ali already talked about the discretized Anosov flow. So discretized Anosov, what is this? Think of time one of the flow. Well, that is going to the flow lines. The flow lines in particular is going to preserve the flow lines, and in particular is going to fix the relief. I'm going to talk about, well, what happens if that's not the case? In the case of homotopy, suppose that this is not L. What can happen? So then L, F of L are connected by a transversal and no other leaves in between. So what do I mean by that? Again, I'm going to draw these actual foliations. So there's a transversal and there's nothing else. In particular, I have a leaf here, which is non-separated from the transversal from L to hyperbolic. So this is not going to be possible. Okay? So the picture is that we have L and two. Let me just talk about the case. So there's an interval. So since they are transversal, there's an interval of leaves connecting them. And this is closed interval. And that's all there is in the region between L and F cube of L. So there's no other leaf here, which does every leaf in between this intersects this transversal. So for I mean the foliation, you know, in the universal cover, the leaf space, in Anosov, you may have lots of things here. And have leaves not separated. This, etc. So let me just talk about the case where there is a transversal. There are an eyeball. Yeah, eyeball, right. So region between L, and that's one way to see is I bundle with I fibers transverse to my lifted foliage. Sorry, I mean it's not exactly eyeball because you could have a temporal lapse something. So in the foliation case, yeah, but then you can have one moderation. Yeah, sorry. Yeah, okay. Yeah. So yeah, I'm sort of forgetting the branching question here, but you could have some LF L here, but you know, I mean it's not so important. It's certainly don't want to confuse anyone. So suppose that there is a transversal here. And let me just explain why you couldn't have a leaf which is sort of non-separated. If not all of them intersect this transversal, you're going to have some leaf which is non-separated from one of the leaves. You could also be one of the boundary leaves. It turns out let's call this E. Turns out that this complementary region here contains balls of arbitrarily large radius. So this is a fact about radius foliations. The complement of any leaf in the universal cover contains very large sets. So I have very big things here. Now, if you act by F tilde, so L is taken here, and then another thing that you would have to prove that it preserves orientation by this ball here would be taken by F tilde of P to something on the other side of F tilde of L. But the second property there says that the distance between a point and its image is less than A0. So if I take the center, it's going to be taken here. Here's this big ball. If I take the center, I'm going to be taken here because this is sort of has to be less than A0. So the image of the point has to be here, but also has to be here. There are many other cases, but this is sort of the main idea here. Okay? Right. So if you have some leaf which is not fixed, then you're gonna have the diagonal in the leaf cell, and then you can iterate. So there's the first trichotomy. I mean, I guess rose here will be the trichotomy. F tilde fixes all leaves. And this case will eventually lead to the discretized amount of flow. F tilde fixes no leaf here. So when I have my L, F tilde of L, and then iterate to the square of L, etc. And then I take that, it's gonna eat all of the universal product. And then F tilde fix some, but not all the differentiation. Right. So in this case here, so the CS is what's called R covered. The leaf space, the leaf differentiation is R. As you know, if you start with one leaf, then it should eat everything. Right. So yeah, so I should say one other thing, right? So if I have this L to the L, etc., iterate, and I limit to a collection of leaves, every leaf here is fixed by F tilde. So I'm not going to explain how this is done. This is fixed by F tilde. Okay? So if there are no fixed leaves, then you know when you iterate by F tilde, some L is going to get everything. Okay? Right. So first, I'm going to explain how to get rid of the case 3 and hyperbolic method. A little bit. I'll do all the details a little bit. And you can get rid of case 3 also, but start by essentially the same ideas for cipher. Obviously, the assumption is that I mean homotopy together. So for M hyperbolic, case 3 and not happen. Right. So, right. So, so in is 3. Right. So sorry, I should say right. So if this is a minimal sublamination or minimal lamination. Yeah, no, sublamination. This so that every leaf of this is fixed. So first of all, that result that if L tilde is not fixed, then there's a I bundle between L and F tilde of L, implies that the set of leaves which are not fixed is open. So the set of leaves which is fixed is closed. And just take sort of a minimal subset of that. Okay. So then there are no fixed points F tilde in any leaf the leaf of this foliation of this sublimation. Okay. And this here is a huge difference between branched and unbranched case. So in the unbranched case, it's sort of very simple to get this. In the branch case, took us 2 months of a summer to get approved, and not a very clean food. Anyway, once you get this, this implies that leaves these are either planes or annuli. And so now I'm going to do sort of the, I think in the case of foliations. So just to draw. The foliation. It's okay because I can also approximate by a foliation, and here I'm not going to use the dynamics. I'm just going to use topology. So I'll take a complementary region. Yes. So the boundary leaves. So the boundary leaves are leaves, you know, in this minimal sublimation, which has leaves which are only planes or annuli. So the boundary leaves are annuli. So now I'm going to draw a picture. This is one place where I'm going to use M hyperbolic. So here is the complementary region. This is in the map. Here is an annulus. And you have sort of what's called an octopus decomposition. I'm not going to get into too much into that, but it means that there's sort of another leaf in which they are very close. So this is an annulus. And you can go around. So this is in here, this is in here, this is in the complementary regions, and annulus which connect. So basically this, from here on, this is going to be sort of an eye bundle thing. And then you're going to have other leaves. Maybe we could connect them with another column. Okay. And you have annulus, and etc. You get a torus. And this is where hyperbolic is used. Now M hyperbolic. This is not I want injective. And you work a little more. This bounds a solid torus. This is a solid torus. And then sort of an argument, volume versus length growth. So eventually we get to a place where we have to go back to the sort of the branch setting because we have to use dynamics. So leads to a contradiction. But the toroidal is crucial because you have to have the stores. I mean, you could have a very complicated thing, a complicated manifold in here, but in the case of an hyperbolic bound solid toroidal. All right, so that means that in the trichotomy for M hyperbolic, from now on, I'm gonna restrict to M hyperbolic. Okay? So now on M hyperbolic. So there are really two options. So F tilde fixes all MCS leaves, or F tilde translates, and this is uncovered. Yes. So furthermore, any two leaves WCS are a bounded distance from each other. That's because the map F tilde moves points about the distance. So here's L, F tilde of L is less than A0. A0 is a bound, upper bound for this between X and F tilde of X. And then you can just integrate it. This is what's called uniform foliation, which will be used later on. Okay, so I have this for the WCS, I have this for the WCU, and then you put those two together. Okay, so the first thing, and this I'm not gonna go in equal. So here, that's the go for yes, yes. M is hyperbolic. No. The proof for branches is a little more tricky, but it's essentially the same thing. It's a volume versus rate. Right. So now put WCS and WCU together. From now on, I'm gonna. So it's the case. One of the cases, I'm gonna sweep a lot of stuff under the rug, even more than I have been doing. Right. So do a lot of work to show no mixed case. So F tilde fixes every leaf of WCS, no leaf of WCU. So I'm just going to say a couple of words here. This would mean that every leaf of WCS is plane or annulus. And then if F tilde fixes every leaf of WC, right. If it fixes here, then we can study the map inside those leaves, in particular inside the annular leaves. And that's sort of like a translation there because it's translation along the CU. And then eventually you get to a couple of leaves. Let me not say more here. So remaining we have two possibilities. One is F tilde fixes in every leaf of the CS, the CU, and two is F tilde fixes no leaf either foliation. Okay. I'm gonna say some things about this case. I'm gonna talk more about this case because it's more interesting and it's more sort of along the lines of the collapse and other flows that we're going to do. So for one, now consider the set of center leaves, which is fixed by F tilde. So there was a question yesterday. I think it was Francois, asking whether we have a leaf here and a leaf here, is the intersection connected? Well, a priori, we don't know. This is one of the things here because, it may fix the leaf L and the leaf U, but the L and U may be lots of leaves, maybe infinitely leaves, and maybe the F tilde is, kind of switching them. So first, show that F tilde fixes all center leaves. So here you sort of split into fixes. So first you show that either it fixes every center leaf or fixes no center leaf. Once it fixes one, you can show that it fixes an open set in the CS leaf containing it. an open set in the C, you look contain it, so it's an open set, then you use sort of a pi one in invariance, because you know the F2 that commutes with every deck translation. So then the set is invariant, and it can sort of fill up everything. So it's either nothing or everything, and in the nothing case, you get a particular everything, all the center views. So then more work. So no branching in the CSD and CU. So it means no branching. So these are actual foliations. And now we're basically in the setup of Bonatti and Wilkinson. This implies that F tilde is a discretized Anosov flow. So in particular, you know, it doesn't fix, it fixes now the center leaves, and it doesn't fix any point in the center leaf. So it kind of is flowing along the flow which is along center leaves, because now the center leaves from the foliation. And Bonatti and Wilkinson's condition show that that implies discretized, which in particular is a collapse on the flow, and it's a strong collapse on the flow. Okay? So this shows SDA. That shows all the LSCAF. It's very easy to see in Quasi-geodesic. Quasi-geodesic is a little hard. All right, so let me spend some time talking about two. So case two, which we call double translation. So it's going to be sort of translation in the CS and translation in the CU. I'm going to do some arguments, won't have so much time, but first I'm going to say, so what's the strategy here? So what we prove, and this double translation is actually work of myself and Professor Tree. I mean, a lot of it was done already by actually with another author, B is Thomas, and one of the F's is Stephen Frankel. So there was a lot of work determining the structure in the double translation. And then myself and Raphael, we proved a little more. What we proved is F is quasi-geodesic Barthelmé hyperbolic. So, right, so here, let's see. General strategy to prove. So I'm going to list a collection of properties which are little by little stronger, and in the end you get this property. So first of all, right, so a pi one of them is not reproducible, so then the leaves of the CS and CU are Gromov hyperbolic. They have one of the conditions for the quasi-geodesic partial hyperbolic. And now, now we see is the center foliation. So we want to show center leaves, and I'm going to do the CS foliation. As WCS leaves are uniform quasi-geodesics. So here are the properties. So the strategy is to prove the properties. So first is the landing. So if C is a ray in a leaf, center leaf, in L, a leaf in the center stable, then C limits. So first of all, C is properly embedded because it's a part of a formation, of a branch formation that needs to be properly embedded. So limits in a unique point in the circumference interval. So L is hyperbolic. Think of it as a hyperbolic plane. So it has a configuration with the circle. Infinity. So here's L. Here's L. And what I want is that here's my C. So accumulated in a single point. Unique. So I say that this length, unique point, let's say P, so lands in P. What I do not want is this. Limits in interval, not point. So I do not want this, okay? Because geodesics are bound because from geodesics, therefore they have ideal points, or unique minimum points. Okay. Second property is so this strategy is actually to prove, tries to prove that one-dimensional foliations in two-dimensional, containing two-dimensional foliation with Rome hyperbolic are by partial depth. Second property is the small visual measure. So roughly means that arcs in leaves the center foliation far away from a point then seen in the CS leaf have small visual, and you can quantify this. So I do not want to see an arc which is really far away from here, my X. I'm looking for the X, I'm looking at this arc in C, which is center leaf. And all the points are far away, and I'm seeing sort of a definite angle here. Okay. I mean, if it doesn't land, obviously it fails this property. But so having the small visual property is actually stronger than that. So this implies geodesic rays with same ideal points are boundedly away from center. I'm doing it for rays, but for arcs as well. So what I mean is that if C is, so if C is a center ray, and now I have the small visual measure, so in particular I have the landing. Okay, so now this property is this, so here's a center ray, and now take the geodesic, right, so take a geodesic R. So, right, so we may assume, just for simplicity, that this has leaves negative curvature, not just hyperbolic, but negative curvature. Just, it is not really essential, but just to get uniqueness of the geodesic ray. Okay. So if this center ray and R geodesic ray on the same initial starting point and landing point, So I guess should be, there is something zero bigger than zero, so that R is continuing in the neighborhood of radius zero, C. So I guess getting half of the property that I want for quasi-geodesic behavior, which is now the geodesic rays are bounded from the centers. I want the centers also to be bounded from the corresponding geodesic rays eventually. Then next property. Why do I need this symmetry? I'll get to it. Right. So right. So what could happen? So Pearl cycle. So this is bad. But right. So this fails this, but you could have here is my ray, but you could have something. And yeah, I mean, this is easier to get than the other one. Okay. All right. Okay. So then have no bubble leaves. So it's no center leaves. Both ideal points the same. So what I don't want is this. So I want to say that this doesn't happen. Then Hausdorff leaf space this center foliation in any leaf interstable. What I don't want is this sort of thing. Okay. Right. Once you get the Hausdorff, so right. So ideal points center rays vary continuously. So not in the same CS leaf necessarily. Right. So let me talk a little bit about this. I don't think I'm going to have time to prove any of these problems. So I'm just going to do sort of the general strategy and say sort of general remark. But right. So this foliation is uniform, meaning any two leaves in universal cover are bounded distance from each other. So each leaf here has a circle at infinity, and they have another leaf here has a circle at infinity. There's a natural correspondence between the circles and infinity. Okay, so this is homeomorphic to S1E. So how to do that? So get a ideal point here, get a geodesic ray. So using that, it's a bounded distance from E, you're gonna get some R prime. So R prime bounded Hausdorff distance from E, and then you use the R cover property in this bounded distance property, show that R prime is a quasi-geodesic, and therefore, if it's quasi-geodesic and is sitting in the a surface of negative curve, which has a unique, it's bound distance from the geodesic ray. And it has a unique limit point. If this is P, this is going to be sort of my P of P. This correspondence is the homeomorphism. Have 5 minutes? Yeah, 5 minutes. Okay. Homeo, sort of yeah, well, I mean, we'll have 10 minutes of talking instead of 15. All right. Pi one of them equilibrium. Anyway, so the sort of identifying all the x1 produces a circle, which is the universal circle. Okay. And when I'm talking about the limits of rays, so what I mean is that if I have a collection of CI rays here, converted to C, and this ideal point here, ideal point PI, converges to the ideal point of P when you identify the circle validity. Okay? Right. So from here, once you get this, it's fairly easy to show now that so there are no bubble leaves. Therefore, if you have any leaf, you're going to have two distinct ideal points, and there's a unique geodesic here. And I'll show that center bounded distance geodesic, which was the other direction of that thing. And once you have this, then sort of a uniform tracking implies uniform quasi-geodesic. So once you have that it's in a bounded distance here, well, the leaf cannot be doing a lot of this, or else because of what we do. All right, so I have 3 minutes to finish. Let me just say a couple. What is the sort of the main tool? Get this properties. So obviously you have the hyperbolic that it's used, but there's one additional tool. So this is covered, M is hyperbolic, and this is transversely orientable. So there is a pseudo Anosov flow. Use another like psi transverse to this relation, which is regulating. So meaning in universal cover, the flow lines intersect all. So any flow line intersects all these. So topologically, you start to see a product. Now the thing that I use is that suppose gamma is periodic orbit of this flow, gamma Q the lifted in the cover, and invariant under G at that translation. So that means that this is my orbit, and then you're going to have stable and unstable. Let me do it for the regular case. So this is stable, this is unstable. So this in the sort of universal circle that's going to be preserved, this is going to be preserved. And the action is going to be that it's going to be sort of pushing this way here and pushing this way here. So this kind of helps to deal with the landing. Landing property is very easy to get, and the small visual property is not so hard to get. The hardware property is the hardest one. So maybe I should stop here. And there are any questions.
Okay, thank you. Are there any further questions? Okay, then, thank you again.